Highrise Building Design Subject Project. Our building is designed by Motive to design the Petronas Twin Towers in Malaysia. This is the outline of our project. Since our building is a double-framed system with special moment frames, we have set the design factor to the figures shown in the table. Seismic load parameter. The design spectral response are set according to the KSC standard. And to obtain the period, we set the height to 400 m and use the abbreviation number 2 because our building is reinforced concrete structure. Wind load parameter is also determined by KBS standards. Vibration number, which is the reciprocal of the cycle obtained in front of the natural frequency, is obtained from the gust factor. And the damping ratio changes the numbers. Next, we're looking for response spectrum functions. Set the response modification 7 as shown in the table in front. And we set max period as 15 second. PGA with a value of 0.2 was multiplied by 2.5 to obtain maximum value. About core wall. At first, when designing core wall, the displacement became smaller. 2 stiffness. Displacement should be between 1/400 and 1/600, but before core reduction, displacement would be 1/1000 and eventually the core size would be reduced. The left side is a core before design and the right side is reduced. The following is the displacement values before and after reducing the core. Our project will include the design of the sky bridge. When designing the sky bridge for the first time, materials were trussed and both ends were pin coupled. The result showed a period of 19254.863 seconds. The result came out strangely. If the two ends are pin connected, the rigidity of the particular part has occurred. We turned the materials into a beam. Then we changed it into a rigid connection on one side and a roller on the other. This is a picture that changed the pin connection to a roller. As a result, the period came out normally. The concept of our project is to compare the results for the structural system with minimal impact of the damping ratio. We compared the results for the structural system with minimal impact of the sampling by setting the damping ratio to 1%. Of the 11 situations, the original data are in the absence of any rescue system with a sampling rate of 0.01. The following are the figures for each displacement x, y, and period. To know the scale factor, this is the dynamic underside shear force value. And this is static underside shear force. Because the building is a twin tower, the two buildings share the ground level, the shear power at the ground level doubles. So static underside shear force will be half in value. After we figure 11 different structural conditions and compare the numbers of the damping ratio 1% to 10%, we decided to have a damping ratio of 7%. And for structural system, add 2 outrigger and 2 belt truss. The following is the displacement XY after setting the sampling rate at 7%. Story drift is okay. This is the dynamic underside shear force. And this is static underside shear force. We will show you the Midas modeling video about outriggers and belt truss. It's a picture of us actually making a model that we designed with Midas. The gold material are show belt truss and there are outriggers in it.